optical sources. So optical source, that is the major component in optical transmitter circuit, and this optical transmitter actually converts the electrical input signal into the corresponding optical signal. And popularly used optical transmitters are like LED or the laser diodes, LD, semiconductor laser diodes. So there are certain characteristics of these light sources, like the first one. So this one must be useful in an optical link. So there should be some characteristics of light source which we need to maintain. So it must be possible to operate the device continuously at a variety of temperatures for many years. Second characteristics is to that means it must be possible to modulate the light output over a wide range of modulating frequencies. Third is for fiber optic. So for fiber links, the wavelength of the output that should coincide with one of the transmission windows for the fiber, which is that fiber which is used in that particular link. So fiber type that is used in that case, so that must be coincide with that transmission of any one windows. Now next is to couple large amount of power into an optical fiber. The emitting area that should be very small. Next, to reduce the material dispersion in an optical fiber link, the output spectrum should be narrow. Okay. The power requirement for its operation that must be low also. The light source that must be compatible with the modern solid state devices which currently used. The optical output power that must be directly modulated by varying the input current to the particular device. Next, better linearity of preventing this harmonics and the intermodulation distortion. It is to be needed, so better linearity must be there. Next, high coupling efficiency will be there. High optical output power is needed, and high reliability must be there, and it must be low weight and as well as the low cost. So these are the major characteristics of a light source in communication. So light emitting diodes, or in short it is called LED. Now conventional PN junction, that is called as homojunction, as same semiconductor material is used on both sides of the junction. Now the electron hole recombination that is occurred in a relatively wide layer. Now as the carriers are not confined to the immediate vicinity of that junction, and hence the high current densities that cannot be realized. The carrier confinement problem that can be resolved by sandwiching a thin layer, approximately 0.1 micrometer, between the p-type and n-type layers, and the middle layer that may or may not be doped, and the carrier confinement occurs due to this band gap discontinuity of the junction, and such junction is called the heterojunction, and the device is also called the double heterostructures. Now, in heterojunction, it is an interface between two adjoining single crystal semiconductors with different band gap, and these are of two types. One is the isotype, another is the anisotype. Okay, so this is the structure of double heterojunction, and here this is the double heterojunction light emitter. So in order to achieve the efficient confinement to confinement of actually emitted radiation, double heterojunctions are used in LED structure. Now, a heterojunction is a junction which is formed, that I have told you, by dissimilar semiconductors. Now, double heterojunction is formed by two different semiconductors on each side of active region. Okay, so it is given here in this diagram. You can all of you can see here. So the cross-hatched region, it represents the energy levels of free charge. So a recombination occurs only in active indium gallium arsenide phosphide layer basically, and the two materials have different band gap energies and different refractive indices also. Now, the changes in band gap energies that create potential barrier for both holes and electrons. The free charges that can recombine only in narrow, well-defined active layer site. So a double heterojunction structure that will confine both hole and electrons to a narrow active layer, and under forward bias, what happened, there will be a large number of carriers injected into the active region where they are efficiently confined. So carrier recombination occurs in the small active region, which leads to an efficient device. So that is the advantage of having this structure. Another advantage of this double heterojunction structure is that the active region has a higher refractive index than the materials on other side, and hence the light emission occurs in an optical waveguide, which serves to narrow the output beam. Everyone mute yourself.
Everyone mute yourself.
Atul Raj, mute yourself.
हमको बोल रहे हैं.
So what I'm saying, so this is a double heterojunction structure. So move on to the next slide, which is based on the LED configuration. So at present, there are two main types of LED used in optical fiber links, and these are, one is the surface emitting LED, another is the edge emitting LED. Now in so both devices used a double heterojunction structure to constrain the carriers and the light to an active layer. And in surface emitting LEDs, what happened? The plane of active light emitting region, that is oriented perpendicularly to the axis of the fiber. But in case of edge emitting LED, that the light which is collected from the edge of the LED, in order to reduce the losses caused by this absorption in the active layer and to make the beam more directional. Okay, so I will discuss it in details. So a surface emitting LED. Here is a diagram. So in this type of LED, the plane of active light emitting region is oriented perpendicularly to the axis of the fiber. Now, a double heterojunction diode is uh, grown on an N-type substrate at the top of the diode um, as it is shown here. You can see in this diagram. Now, a circular wheel is etched through the substrate of the device, and a fiber is then connected to accept the emitted light. Now, at the back of this device, that is a gold heat sink, and the current flows through the p-type material and forms the small circular active region, resulting the intense of the beam of the light. So here this circular area, it has some diameter, like 50 micrometer diameter is there, and the thickness of this circular active area is like 2.5 to 3 micrometer, and the current density also few thousand, so 2000 ampere per centimeter square, half power of this. So emission pattern is also here considered as the isotropic connection. Now, the isotropic emission pattern from the surface emitting LED is of like this Lambertian pattern. Now, in this Lambertian pattern, the emitting surface is uniformly bright, but its projected area, which diminishes the angle as the cos theta, where theta, that is the angle between the viewing direction and the normal to the surface. Okay, and the beam intensity, that is maximum along the normal. So if the power is to be reduced, it is reduced to 50%, half of its peak, then the angle must be like 60 degree angle, that theta value will be 60 degree. And the radiation power decides the coupling frequency, the coupling efficiency of this type of LED. Now, in case of edge emitting LED, so here, in order to reduce the losses which is caused by the absorption in the active layer and to make the beam more directional, the light that is collected from the edge of the LED, and such a device is called as edge emitting LED, or in short it is called ELED. Now, it consists of an active junction region, which is basically the source of incoherent light, and two guiding layers. So here the refractive index of these guiding layers is lower than the active region, but higher than the outer surrounding material. And that's why a waveguide channel is formed, and optical radiation is directed into the fiber. Now, this edge emitter pattern, this emission pattern is more concentrated or more directional, providing improved coupling frequency. And the beam is here the Lambertian in the plane parallel to the junction, um, but diverges more slowly in the plane perpendicular to that particular junction. Now, in this plane, the beam divergence is very limited, and in the parallel plane, there is no beam which is confined, and the radiation is just like the Lambertian radiation. Okay, now to maximize the useful output power, a reflector must be placed at the end of this diode, which is opposite to the emitting edge. Okay, now there are different features of this type of edge emitting LED, like there must be linear relationship between optical output and the current. Here the spectral width that is to be maintained within the 25 to few hundred, means the 400 nanometer. Modulation, also the modulation bandwidth, which is much large in this case, and it is not affected by catastrophic radiation of the mechanisms, and that's why it is more reliable to use. It has a better coupling efficiency than the surface emitter, and also but it is very temperature sensitive. Okay, so where we can use this type of LED now, basically these are suited for short range, narrow and medium bandwidth links, and where the it is suitable for digital systems up to 200 megabyte per second, and it is used for long distance analog link also. Okay, now move on to the next slide. So here the light emitting semiconductors, few materials has been mentioned in this table, where the wavelength range is mentioned and the bandgap energy is there. So it is some materials like aluminum, gallium, indium phosphide, or gallium arsenide, or aluminum gallium arsenide. So this type of material can be used to make this type of LED, and bandgap energy for each material is look like this. So the spontaneous emission due to this carrier recombination, basically it is called as electroluminescence, and to encourage this electroluminescence, it is very necessary to select as appropriate semiconductor material. Now the semiconductors, depending on energy band gap, that can be classified as direct band gap semiconductors or indirect band gap semiconductors. Now in direct band gap semiconductors, these are most useful for this purpose, where the electrons and holes on either side of band gap have same value of crystal momentum, and hence the direct recombination is possible there. Okay, but in case of indirect band gap semiconductors, the maximum and minimum energies occur at different values of the crystal momentum, and the recombination in this semiconductors, in indirect band gap semiconductor, is quite slow compared to the direct band gap semiconductors. So the active layer semiconductor, it must have a direct band gap, and in direct band gap semiconductor, electrons and holes can recombine directly without need of third particle to conserve this momentum. Now in this type of materials, the optical radiation is sufficiently high. Okay, and which type of materials can be used to make this, like aluminum, gallium, indium, or the arsenide material. So this type of material can be used. Now quantum mechanical relationship between the gap energy and the frequency. Here it is given as based on the gap energy as well as the frequency, it is given as E equals to h nu, where E can be calculated from this one, h c by lambda. We know that nu equals to c by lambda, and from this equation we can find out the length of the light using this equation. Now this energy E represents the energy which is in joule, and wavelength, that is in meters. So now expressing the gap energy in electron volts, which is Ez, and wavelength, that is in micrometer for this particular application. So, and the equation can be written like this. So different materials and alloys have different band gap energies. Now to find out the quantum efficiency and power, some relations must be maintained, and that can be used to calculate this efficiency and power. The total, the internal quantum efficiency, this one, eta int, that is defined as the ratio of radiative recombination rate to the total recombination rate, where this radiative recombination rate is mentioned as R small r, and R small nr is the non-radiative recombination rate. So the total rate is the summation of this one, and so that is the ratio between the radiative recombination rate and the total of this recombination rate, and it is called the internal quantum efficiency. Okay, now if the n are the excess carriers, then this radiative lifetime, which is can be given over here for tau r, which is equivalent to n by r, and for non-radiative lifetime it will be tau nr. Okay, so this can be this is misprinting here. So tau nr, which is equivalent to n by r nr. Now the internal quantum efficiency, which is so can be calculated from this equation here in this way, and the recombination time of carriers in active region, if it is considered as tau, then it is known as the bulk recombination lifetime and can be given using this equation. Now, sorry, from this equation, the quantum efficiency, internal quantum efficiency can be calculated here, eta int equals to tau by tau r. And if the current injected into this LED is I and the Q is the electron charge, the total number of recombination per second can be given as I by Q. Okay, and from this equation we can write it here. We can write it as this one. Okay, so the optical power can be generated internally in LED, that is given as P internal, the internal power, which is equivalent to R H nu, and from this equation it is calculated as P int equivalent to, or it which is equal to eta int HCI by Q lambda. So this is very important, this equation. So you need to write it down, the full quantum efficiency and power calculation. Okay, that's why I have told you you need to write it on your rough copy or any paper. You have to use it. So all of you must write down these equations because we need this later After a few slides, there's a problem based on this equation, and you need to solve it using this equation. So all of you must write down it. So that is the external efficiency equation, and from that equation we can find out the output, optical output power, and this is the optical output power equation. Okay. Now this is the problem. So different advantages and disadvantages of LED. So there are lots of advantages, like simple, it has a simple design, and the manufacturing process is very easy. System integration is very easy and simple, not the very complex. It has low cost, high reliability is there, but there are certain disadvantages also, like refraction of light at this interface, semiconductor and air interface is present. And another is the average lifetime of a radiative recombination is only a few microseconds and a few nanoseconds. That's why the modulation bandwidth, that is only a few hundred megahertz. It has low coupling efficiency, as well as it suffers from large chromatic dispersion. Okay, so these are the different advantages and disadvantages of LED. Now coming to the laser part, laser diode. What is that? It is a light amplification by stimulated emission of radiation, the full form of laser. And it is a device which amplifies the light. Okay, so the operation of this device that may be described by the formation of an electromagnetic standing wave within a cavity. Cavity means the resonator where it is to be happen, which provides an output of monochromatic, highly coherent radiation. Okay, so what is the principle behind this? So there are three fundamental processes occurs between uh, the two energy states of an atom. One is the absorption, another is the spontaneous emission. Stimulated emission is the third one. Now this laser action, it is the result of these three processes: absorption of energy packets, means these photons, spontaneous emission, and the stimulated emission. Okay, so these processes are here given by the two energy level diagrams. So here E2, you can see from this diagram, E2, that is the higher state energy level, and quantum theory states that any atom exists only in certain discrete energy state, absorption or emission of the light that causes them to make a transition from one state to another. Okay, and the frequency of the absorbed or emitted radiation, if it is so it is related to the difference in the energy. And if we have to consider this frequency is, assume this is F and energy is E, then so if E1 is lower state energy level and E2 is higher state energy level, then we can see, we can say that E equals to E2 minus E1, which is the combination of the h into f. H means the Planck's constant, which is obviously the value that is 6.626 into 10 to the power minus 34 joule per second, and the frequency which we have to consider, that radiation frequency of the absorbed or emitted radiation. So an atom which is initially in the lower energy state, when the photon with energy that is E2 minus E1 is incident on the atom, it will be excited and it goes into the higher energy state E2 through the absorption of the photon. But when coming to the next one, so when the atom is initially in the higher energy state E2, it can make a transition to the lower energy state E1, providing the emission of a photon at a frequency corresponding to what I have told you, that E equals to the combination of H into F. So in this way, the emission process can occur in two ways. Either the atom returns to the lower energy state in a random manner, or by, so that is called the spontaneous emission, or by stimulated emission, when a photon having equal energy to the difference between the two states, that is E2 minus E1, and it interacts with the atom, causing it to the lower state with the creation of the second photon. Okay, so spontaneous emission here, it gives the incoherent radiation, while the stimulated emission gives the coherent radiation, and hence the light associated with emitted photon is a same frequency of the incident photon and in same phase with the same polarization, because we know that the coherent source means the source of light that emit waves which have zero or constant phase difference and the same frequency, and just opposite to this one is incoherent source, where the light that emits wave which have the random frequencies and the phase differences. Okay, so if these are in same phase and same polarization, that means when an atom is stimulated to emit light energy by an incident wave, the energy can add to the wave in constructive manner, and the emitted light is bounced back and forth internally between two reflecting surfaces. Okay, so this so for expression to calculate the expression for energy density in terms of Einstein's coefficients, we have to consider this: if N1 and N2 are the two atomic densities in the ground state and as well as the excited states, then rate of spontaneous emission can be given as the A21 N2, and rate of stimulated emission is B21 N2 to UV, and rate of absorption is this one. Now in thermal equilibrium at temperature T with frequency N and the density is considered as UV, and let N1 and N2, these are the number of atoms in energy state 1 and energy state 2 respectively at any instant of time, and the number of atoms in state 1 absorbs a photon and give rise to absorption per unit time. That's why for equilibrium concept it is given as the rate of absorption, which is equivalent to the combinations of this rate of spontaneous emission plus stimulated emission. And from this equation we can find out, we have to calculate the energy density UV using this one, And from now we know that the relative population of label E2 with respect to E1 can be written as N2 by N1 equals to e to the power minus E2 minus E1 by KT. So here from this equation can be written the energy density equivalent to A21 by B21 into B12 by B21 e to the power h2 by KT minus 1. And if we have to consider the black body radiation, the Planck's law, and if we compare them, okay, so there is equation for black body radiation, and if we compare them with this one and this one, we can get it as A21 by B21, which is equivalent to 8 pi h nu cube by c cube. And by comparing the coefficient of the exponential term, we can get it as 1. And after that, from this equation, if both constants, these A and B, these are the Einstein constant, and if this B12 equivalent to B21, then we can write it down that this has been neglected, and the final expression for the energy density in terms of coefficient, in Einstein coefficient, can be written as this one. Okay, so this is the main equation. Okay, and that is the expression for energy density of radiation in terms of Einstein's coefficients. Okay, so next is the laser diode. So semiconductor diode laser. Now the working of this semiconductor diode laser, that is similar with the LED, like the recombination of electron and the hole in the depletion region, if it is forward biased, then the PN junction emits a photon of characteristic wavelength. Now, if a large forward current is flowing through that diode, like this, the population inversion is established between the Fermi levels of p-type and the n-type semiconductor, and hence the lasing effect is achieved using the suitable resonant cavity. Now, in case of LED, what happened? It was, so it is the spontaneous emission of photon that gives the light, whereas in semiconductor diode laser, it is the stimulatively emitted photon that gives the light. Okay. Now the familiar intrinsic semiconductors such as silicon, such as germanium, these are indirect bandgap semiconductors, and the electron hole recombination, that is easier in direct bandgap semiconductor, these type of semiconductors. Okay, so we have considered here the gallium arsenide semiconductor diode laser. So it is the direct bandgap intrinsic semiconductor. So this type of diode, it is obtained by single crystal of gallium arsenide doped with zinc and tellurium to get the p-type and the n-type this gallium arsenide semiconductor diode respectively. Now the doping is so high that there are few thousand atoms per centimeter cube doping can be implemented, and the sandwich of this p-type and n-type, this forms a diode. So here two faces parallel to the so these two faces, basically this is parallel to the junction, which are provided with this metallic contacts to provide proper biasing. Now a pair of opposite faces that is perpendicular to this junction is well polished, or that is called the clipped faces, and the remaining a pair of opposite faces perpendicular to the junction is these are roughened spaces. Okay, and the refractive index of this gallium arsenide with respect to here is very high, so that this polished faces serves as the resonant cavity. Now the working principle here, it is given by these two energy level diagram, which is for before biasing and after biasing. Now in the absence of biasing, the electrons of n type that can cannot cross over the junction because of the potential barrier. Now when the diode is forward biased, the charge carriers are injected into the depletion region, and a large current flows through the diode as it heavily doped. Now the population inversion is achieved in this way at the depletion region between the electrons and holes, and this recombination of the electron and holes in the depletion region basically emits a photon, stimulatively emitted photon. Now this photon is reflected back into the depletion region at the polished surface, polished faces, and stimulate the recombination. So these stimulatively emitted photons are basically multiplied in the resonant cavity, and after sufficient amplification, it is an intense laser beam which is generated, which is emitted from this surface, this polished surface, which is having very relatively low reflectance characteristics. Okay, so that is the working principle of this type of gallium arsenide semiconductor diode laser. So there is a comparison between this LED and laser. Some has so LED has certain advantages and disadvantages. Also, the laser has some disadvantages and advantages. Now, for LED, low efficiency is there, and for laser, it has high efficiency. For LED, the slow response time is there, but in case of laser, it has very high or fast response time. For LED, lower data transmission rate, but in case of laser, it has high data transmission rate. LED, for LED, it has the advantage of broad output spectrum, but in case of laser, it has the disadvantage of having the narrow output spectrum. Okay, LED incoherent beam is produced, but in case of laser, coherent output beam is produced. In case of LED, low launch power is there, but in case of laser, the higher bit rate is to be achieved. High distortion level is there in LED, and LED laser has less distortion. Okay. LEDs are suitable for shorter transmission distances, but laser is used for longer transmission distances. LEDs are less temperature dependent, but lasers are more temperature dependent. LED simple construction, laser has the complicated construction. For both of them, it has the lifetime of 10 to the 7 hours for LED as well as for laser. Okay, so that's all for optical sources based on the LED and the laser.